there's one that's yep, yep, yep. Okay, so this is the presenter. Right. So this is the presenter. Testing 1, 2, 3. Yes. Okay.
microphone. Okay.
And then just bend it until it's just touching the side of the, something like that.
Like that?
I'll go back here and get my earphones on and then say
Okay. Is it turned on? Huh? What are you looking for? I have it in my pocket. I lost it, and I spent about 10 minutes looking for it. I put it in my bag. Maybe I'm going to pass these out. Put a couple here. David, could you do these? Oops, sorry. Get some of these here. And maybe pass those down. Pass those down. Did I give you enough there? I think I'm shy there. Am I shy? We're okay? I'm going to go get some more. There's 3 of those. Let's see, I think I've given you too many there. 3 here. Yeah. Oops, I'm sorry.
And Gary,
Yeah.
I just inserted that slide in yours, so it is your presentation.
Oh, okay.
But feel free to switch over to your title.
No, you're gonna start with an intro, right?
Yes, I.
So that'll be your slide. Now.
Okay,
So,
sound test 1, 2, 3.
can you hear me? Here I am. Yeah. Okay.
All right. Don't, we're quite ready yet. Do you know the name of your talk, Sifan? I don't have it on this paper. Pan stars. Okay. So, what time? Do you know what time?
Yeah.
Do you know what it is?
How many
It is
more?
6:15. Okay. All right, I'm going to get JD to gather whoever from outside. Great, thank you. Thank you.
They don't come. We have to let other people in here.
Okay.
Yeah, but we have to. We're starting now.
Hi, Don. How are you? Good. How are you?
Yeah.
Oh, I'm emceeing tonight, and I'm giving a
Let
lecture at
other
7.
people in.
So we're wired. It's live lectures, live stream. So we have 4 lectures, but welcome and the lectures.
Oh, you're emceeing the lecture.
Yes, yes. We'll start one in a minute, and there's a list on the door. I don't know where the list is of lectures. Oh, let's see, right here. No? List of lectures hanging up here. So
I'm not sorry, but you can get them on the internet.
I think we're about to start if you want to funnel
Is
anybody
there a
in.
store on this island? I guess not. But you can get them on Amazon or on my website.
Doing on. Good. I'm glad to see you, Don. Do you have any interest? Microscopy. His interest is the first it's about to start. I'll leave that to announce, actually. Okay, it's a full house, huh? Do we have overflow upstairs, JD? JD? Excuse me. Hi. JD? JD?
You know, these people aren't showing up, so I think we have to get yeah. Should we get 3 others? Because
If anybody wants to see a lecture, we're going to start. Okay. We'll just close it a little bit. Is it too loud for you guys in back with the door open a little? Can you hear okay? Okay, great. We're going to start. Hi, my name is Dr. Joe Ritter. I'm the laboratory director here at the Institute for Astronomy. What we do is remote sensing. We measure things from a distance. So my friend Dr. Gary Greenberg is a biologist who has developed novel, patented, amazing 3D technology for microscopy. And you would say, what does that have to do with astrophysics? It's remote sensing. So Gary, Dr. Greenberg, has a PhD in developmental biology. So another common thing. I used to work in developmental biology, but Gary is a real PhD in it. He invented 3D microscopes. He is an author of many books, including books on sand. And does really the most amazing microscopy I've ever seen. He had the cover of Microscopy magazine, which if you're a microscopist, you know, that's it, right? He's a TED speaker, and together we are recipients of a NASA grant to study sand on the moon, where we're doing scanning confocal Raman microspectroscopy along with 3D morphology with his amazing microscope. So without any further ado, Dr. Gary Greenberg.
thank you. Thank you, Joe. Now, can we turn the? We're going to turn the lights. Okay.
Up here?
These here, huh? Great. Good. And then I will still be in the light because I'm going to be here. No, thanks. So you won't need the 3D glasses until a little later. But when you do put them on, when I tell you to put them on, the red is on the left. So fold them in the direction so that the red is on the left and the yeah. So but first I'm gonna talk about sand grains, and sand grains are not only on the Earth, but they're also ubiquitous all around the entire universe, including in outer space. So these aren't actually stars, but that's star sand from Okinawa, and these are little grains of sand, and you can see them live under the microscope in the microscope lab a little later. And these are little foraminifera. They're actually the tiny houses of little protozoa. So sand, this is sand from Maui, Hawaii. This is some of the first sand that I've ever looked at. And I was amazed when I saw what sand on Maui looked like. I thought it was just little brown rock. There's all amazing things in the sand, especially in Maui. There's lots of biological stuff. Um, there's things like sponge spicules and bits of sea urchin spine and little micro shells and shell fragments, stuff from the volcano. A lot of totally amazing things. And when I saw that, I really got hooked on sand and started looking at sand. Most sand in the world comes from the erosion of mountains. So being remade, mountains are being built up and they're eroding away into grains of sand. It takes a long time, but it actually happens. And mainly water and ice and forth. So this is a fall. These waterfalls are bringing sand down into rivers that then go into the oceans. You might wonder, well, how can grains of sand actually erode away from rock? If you look at rock in a microscope and you look at little tiny, what rock is actually made of, you can see that they're made of all little tiny grains of different minerals. So what happens is when the temperature freezes and thaws or water hits it, these little grains of mineral are liberated. And these are grains of sand from Big Sur in California. And they get more and more eroded and rounded away until they finally disappear into silt and clay. So this is some amazing sand. There's a green sand beach in the south point of Hawaii. That's a big olivine outcropping, and that entire beach glistens this beautiful, beautiful green grains of sand. They're totally amazing. You can see some of the little bits of sand from the volcanic sand as well. This is sand from the Galapagos Islands, and it has a lot of interesting mineral grains. Most of the sand in the world, or not most, but the highest percentage of sand in the world is made of quartz crystal, because most of the rock in the world on the earth is granite rock, or a lot of it is granite rock, and when it erodes away into quartz crystal. This is very, very fine quartz crystal. There's no other things in it like feldspar and other sorts of minerals. And it's these sorts of really, really pure quartz crystal that make things like glass, computer chips. Sand is used in concrete. So in this room right here, we have the concrete walls, the glass windows, and the computers that make all this running. It's all made from sand. People say, well, is that what sand really looks like? The answer is, in science or in anything in the world today, when you look at things, you see what you see depends on what you're looking at it with. So this is sand looking with reflected light. This is the exact same sand looking with light going through it. So you can see the difference. This is reflected light. This is light going through it. It looks completely different. So when you look at things from different points of view and different lights, in a different light, you learn different things about it. The original sand in the universe was created by exploding stars. This is an exploding star, and that's where the first sand in the universe was created. Stars burn hydrogen into helium and then make the heavier elements, and when they explode, little tiny dust particles and grains of sand are formed. Also, the universe is a very violent place, and things are knocking into each other all the time. This is a little rendition, an artist's rendition of what it might have looked like when the moon was originally formed. So the moon was formed by a collision of about a Mars-sized object to Earth about 4.5 billion years ago. And all that debris went around to form the moon. And one of the reasons we know that is because the constituents of the surface of the Earth and the isotopes of all of what we find on the moon are the same. If we look at other things like meteorites and other planets, there are different isotopes and different combinations of minerals. But the moon and the surface of the Earth have the exact same constituents. So that's how we know it was formed by an early collision. So all this sand is in outer space, and you can see it when you see a falling star. I'm sure we've all seen shooting stars. They're actually little grains of sand. I know it looks like it's really bright and lit up, but for the most part, they're little tiny grains of sand that are going 18,000 miles an hour, and it's igniting the atmosphere. So the air is actually glowing, and that's what you're seeing when you see the falling stars. So these are micrometeorites. They're the size of little tiny, tiny grains of sand. And they come in all sorts of shapes and sizes. Some are, this one I'm going to show you a little later. You can see right in the middle of it. You don't need your 3D glasses yet. Here it is tilted a little bit. You'll see that better in 3D. There's one that's was a crystal and it's almost completely melted. So I want to show you a little bit of moon sand. Dr. Joe Ritter and I have been looking at sand from the moon. This is where they first landed in the Sea of Tranquility. And you see those dark areas on the moon? Those are actually lava flows. About 6.5 billion years ago and earlier on the moon, about 3.5 billion years ago and earlier on the moon was still volcanic. There are volcanoes, and these large lava flows can be seen. We call them the oceans or the seas. Now, if you look at the backside of the moon, there's no lava flows on the backside of the moon. You know, there's only one side that we see. The moon and the Earth are kind of locked together, so we only see the front side. But when we went around looking at the other side of the moon, we noticed there's none of these. It all looks like this. It all looks cratered. The backside of the moon is much thicker than the front side, and there are various theories that explain why that might be. So I want to talk a little bit more about how in science we see things from different points of view. Moon sand, looking at with three different microscopes. This is looking with a 3D light microscope, and you can see parts that are opaque, parts that light up. You can see colors. This is the same grain of sand using a scanning electron microscope. You see the surface really, really well, and you see things you wouldn't see there. Here's the same grain of sand looking with an X-ray microscope, and you see again a completely different thing. So in science, what we do is we look at things from many points of view, and we build a model of what it actually looks like. Here again is that same grain of sand, and you can look at it from different angles. The backside may look completely different from the front side. So this is what science is about, looking at things from many points of view and then creating a model of what it looks like. So this is sand from the moon, and you notice there's a hole here. A micrometeorite went about 18,000 miles and just drilled a tiny, tiny hole into that grain of sand and melted it into a new grain of sand. There's lots of grains of sand on the moon that have holes in the middle of them. And that's very characteristic of sand from the moon. There you can see it. And here you see the same grain of sand but turned on an angle and looking from a different angle. And you see that hole in the middle. And a lot of the grains of sand from the moon were formed by a great amount of pressure, temperature, that made things. So this little tiny grain of sand has at least 4 different types of minerals all squeezed together in one grain of sand. There's a lot of glass on the moon because bombardment on the moon creates glass because of the heat from the bombardment. Little grains of glass are formed, and then they get shattered again. And the different colors have to do with the different temperatures and the different minerals that are there when the little grains of glass were formed. And then they all get broken up again in little tiny pieces. And the sand on the moon is very dangerous to breathe, and it gets in all the workings of the spacesuits. So one of the main challenges for going to the moon is learning how to deal with moon sand and moon dust. Here's a single grain of sand from the moon, formed about 4 billion years ago, and it still has its whole crystal structure. Now that's the microscope I use to take these. Put on your glasses so the red is on your left, and we'll look at a couple of these things in stereo 3D. So that's that same grain of sand, but now you can actually see the crystal structure of it. You can see the parts sticking out. This is a big indentation that sticks out at you, and you can see. Are you guys can you see that? Good. Okay. So you can see when you look at 3D, you get more information. So in science, we try. That's again that other grain of sand that I was showing you how we look in different ways. Well, now we can see it in 3D. We see what the depth of each of these little particles are that make it the constituents of it. So these are all this is from the Apollo 11 mission from the Sea of Tranquility, and so is this. And you can see the pressures that have occurred to make these things fuse together, these different minerals fuse together. Here's another example, one where this one wraps around the backside and all got fused together. This is a number of different minerals. There's a bit of a glass there with probably iron rich. Now this is interesting. This is a grain of sand from place called Trinity where they did the first atomic explosion. And this was a regular bit of quartz sand, but the temperature and the heat from the atomic bomb, you can see what it did to all these bubbles and the stress in it. And a lot of sand from the moon has a lot of incredible stress too because of the collision from which it was originated. These are a handful of little tiny micrometeorites from outer space. You can see some you can look right into the middle of. Here's looking closer. You can see right inside. This is tiny. This is a tiny grain of sand from outer space that was once a shooting star. It landed in the South Pole, and the Army collected them and sent them to me to photograph in 3D. It's so small. It's a half a millimeter. It's less than a half a millimeter. Really, really small. Yeah, you can't see. I mean, you need a 3D microscope. People generally into sections, then you never know what it really looked like. So we're using these microscopes that I developed. You can really see it in 3D. Now, this is a grain of sand from Corsica. This is biological, so we're coming back to Earth here. And we're ending up with the star sand. So just to remind you that there's sand in outer space, and this is sand from Okinawa, Japan. And I think that's it. That's my latest book, which has sand from the moon and so forth. So thank you very much for your attention.
Thank you, Gary. That was great. And we'll take a short break. And no time here, and I don't have to keep off the building. During this 5-minute break, we're going to open windows and stuff like that. Next stop will be Seapod, who's helping us actually doing all the audio-visual stuff with that. Tell you about stars, which is a telescope. I'll tell you a little bit about it. I'll tell you all about it. And comets that could hit Earth. Protect people. I mean, a lot of that'll happen at let's see, at what time? At 6:40. 6:40. Okay, so in 8 minutes we'll have one more talk.
Yeah.
That's better. Okay. Let's see here. Testing 1 2. Testing 1 2. Hello, hello. Okay. There we go. Right about there. Okay. My talk will be starting shortly. It's live. Joe? Yeah. Is it on?
Congress mandated to NASA that they should go find objects above a certain size that would hit Earth and a certain number, a certain fraction of them. And they didn't do it. And then people from the university said, well, we really want a big survey telescope for looking at astrophysics and where things are, but we could find a large fraction of these objects and very small objects to make sure we see where they're going and see if these things would hit Earth or not. And I won't tell you much more because we have an expert that helped us develop this whole system here. And so I'm going to introduce Stefan Kahale. And Stefan graduated from the University of Wisconsin with a degree in chemistry. So our last speaker was a biologist. And Stefan is chemistry, and you'll hear about me later. And it's also not astrophysics. And performing research for the university hospitals, she was instrumental in developing 2 of the analysis procedures of the first commercial automated clinical analysis machines. She then started and was the CEO of a small corporation that designed and manufactured what we now call PCs. These were used by the university for clinical chemistry automation, and it launched her career in computers and IT, and eventually becoming the director for an international training division, having classrooms in over 20 countries around the world. In fact, her name was given to her in Beijing. She's always been involved in astronomy, having built and fully automated a number of her own telescopes from scratch. And today, Stefan handles the summit and control room computing for the Pan-STARRS telescope, is a member of the UH steering committee for our virtual classrooms and outreach, and is one of the observers for the Pan-STARRS telescopes. She's responsible for the IFA's virtual presence in numerous online worlds. And this should be a really interesting, this is a unique instrument. There are no other telescopes quite like it. This should be an interesting talk. So please welcome Stefanka Holly.
Thank you.
And you're okay on lights, I think? Like
Yes,
this? Okay.
this is great. I think everybody can see it okay. I don't have any very beautiful shots like Gary just did with the sand. I wish I did, but you know.
And will you want questions at the end, or
At the end,
Okay.
yes, please, because
I should have asked
it's
Gary.
very short
Okay.
with what we're doing here. And like all of our talks that we give here, they're all video cast both to the web and also to virtual worlds like Second Life, In Worlds, Metropolis, and a number of other ones. And so one of the things I had better do is say hi to my virtual audience, because they never see me up here. They just, I'm in worlds with them talking and chatting, but they never have seen me live before, so hello. Or I should say aloha. So I started about 8 years ago here with the Pan-STARRS Observatory. You know, as Joe was saying, the main purpose, well, actually, in the very beginning, it was put together by a consortium of about 12 to 13 different organizations around the world. Each organization came together and proposed a main mission. And out of that, it reduced down to about 12 of the 12, reduced down to 6 major missions. One of those was a survey of the entire sky, the entire visible sky that we can do here. Every time you do, say, take a complete picture of the entire sky, you call it an epoch. We are on epoch something like up in the 20 billions. The unique thing about this, that this brings along, is sort of a new, different area of astronomy called time domain. And what's beautiful about this data that we now have collected for all these years is if something goes pop tonight, let's say we have a supernova, and by the way, we're detecting them about once a night. Let's say we have a supernova that goes off. Well, what was that beforehand? Was it flaring beforehand? Was it brightening and dimming? Was it doing weird stuff beforehand? Or was it just sitting there? Up until Pan-STARRS came along, you couldn't ask her that question. Because the second the star went boom, everybody goes, oh my goodness, there's a supernova out there. Everybody shifts their telescopes over to it, takes all the data and images from it. But they can't go back in time. So what we have compiled, and by the way, our databases right now, the complete index of everything we have is close to 3 petabytes. A petabyte is 1,000 terabytes. So to give you an idea, that's one copy of our data. We keep at least 3. We're building a 4th one right now because we're about to move our compute facilities over to the Big Island. So we're having one that we're going to keep right here. So there's a lot of data. And as a number of people have said, there's gold in them thar data. You know? And that's just one idea, one example of how scientists are using this data, that we're creating. So of all of these surveys and missions that they came together, the 6 major missions, a couple of them were the sky surveys that we're doing. None of those were actually looking for NEOs, near-Earth objects. Those are asteroids and other things that are going to hit us or come close to us. Okay, but it turns out that when you're doing this survey, and here's the unique thing: it's not just a survey; it's a repetitive survey. So that way you can a picture from tonight, and take the same picture tomorrow night, and then subtract the two. If you subtract, remember, stars and the image, everything's numbers, right? So you have a star of a brightness of a certain amount, and you subtract tomorrow's image, a star of the brightness of the same amount, going to go 0. So anything that's relatively stationary is going to go away. So what's left? Things that move, because you have a spot where it was today and a spot where it was yesterday, and I'll show you some slides of that. And so right away, aha, we've got something. And the second thing that might be is if something brightened. Supernovas, right? Or if something dimmed. Maybe an exoplanet or something going in front of a star, okay? And I can go on and on and on. So this is a beautiful engine for finding these kinds of things. And like a story I always tell when people ask, our job, well, then you get excited and you follow up and all this. So no, here upstairs, we hardly know, because this all takes place with a tremendous amount of processing that goes on down in Kihei. In fact, I've got 32 racks. Each rack is a little bit taller than I am. Each rack holds, maximum is about 42 computers. Each computer has about anywhere from 8 to 32 cores, CPU cores in it. Do the math, it's some huge amount of processing cores. And then in addition to this, all the data disks that we have, some of our computers hold 48 disks. Each of those disks is now 6 terabytes. So it's massive, it's huge. It's called a data processing pipeline, the IPP. Okay, the imaging processing pipeline. Now, in computer terms, a pipeline is something where you take something in the front end, and you need to process this in such speed in order to get it through. In our case, because the next image is coming down line. So you need to do this in a quick enough amount of time so you don't have time really to save it on disk. You can't take it into one computer, process it, save it, and the next computer takes it up. No. It's flowing from processor to processor until it comes out the back end and is saved. Even with this, they will start, in fact, we've just opened up, so the telescope's open, it's taking images right now. And when you're done, you can go up you can go up and see Angie. She's the observer tonight. I get to go on tomorrow night. So, the IPP is now opened up, and it's receiving these images that are coming down from us right now. And it's going to do this all night, and it's going to take until about 2 or 3 o'clock tomorrow afternoon for it to be completed. So it gets like a couple hour rest, and then boom, off it goes again. So it's very fast, very huge, a lot of compute power, and that's down in Kihei. So with that in mind, let's take so we're watching for these things. Now this is a bit of a scary kind of picture, but I think it was sort of cool. My boss, Ken Chambers, found this one. I thought it's what he uses for his. This is the top of Haleakala. This is the erosional feature. Can't call it a crater because it's not a crater. This is the ridge coming up from Poli Poli, and this is an old shot, but this is Pan-STARRS right here, at the edge. Right here is the park headquarters, and or the park, the park at the very top. This is Red Hill, where you go up and you can circle around and see things. And we normally the winds are coming from this direction, so we're aiming our telescope off this way. So when we open up the telescope, we see all these people over on Red Hill looking back at us going, as our dome slowly opens up. And yes, we have cameras all over the place, that are in here. I'll tell you a little bit more about that too. So that's you have to look, one of the requirements for operating remotely, which is, as any observer will tell you, is that a blessing to be able to sit up here in a nice warm office where you can have the lights on, you have a kitchen, restroom facilities, everything else. Whereas at the summit, when in fact, that was my first task that was assigned to me. In my background experience, I've consulted for a number of top 500, Fortune 500 companies in how to put together robust, what we call production environments. In other words, 24/7. Anything goes wrong, something else takes over, etc. Right? And so I was hired on to do two things. When I first came here, one was to take this engineering project, this university project, and operational is sort of a foreign word. Right? So it's to take that and make the changes and everything else is necessary so that this can continuously run. And what's this, 9 years now that it's been going. So, and the second thing second task I had was to automate it so that we could run it down here. To make sure that I was motivated, they made me an observer. So I had to sit up here, and let's see if I've got the next here. I had to sit up here in this building here. This building is Um, I think there's probably more holes than so the wind goes right through you. So can you imagine 14 hours a night in this freezing building? You can't turn on the heat because hot air is going to rise and get in the way of the telescopes. You can't turn on light because where the wind's coming through, the light is going to go the other direction, right? And you have to stay there for 14 hours in this dark, very cold night, especially in winter. I think I probably automated it in record time. Talk about motivation. I was very, very motivated. So we have an observer that just went on for something else. That she moved on, and so now they've put me back into service. So that like tomorrow night for 4 nights I'm going to be I'm observing again. But at least that's here. And you're welcome to go up and take a look at our facilities up there. When you're done. Let me go back one. This is we're a survey instrument. In other words, our job is not to look at anything specific, but to go across the sky and survey. And I usually explain this to people when I give tours and things, as imagine back in the old days of the cowboys and the Indians. When you had the troops go out, okay, they had scouts that went out in front of them. Okay, the scouts do not engage the enemy. They get wiped out. Right? We're the scouts. Okay, so we're out there, and our job is to keep looking. If we find something, it's not for us to go back and look and check. We're going to miss something else. So our job is just to keep going and sort of throw it over the wall, kind of, so to speak. And so I always say the big boys on the big island with the big telescopes, they take it over from there, as well as other places in the world, and then track down whatever it is that is interesting within our data. But our job is to keep going. So it's a survey, and it's a panoramic, and I'll talk a little bit about that here too. And the rapid response, and what that means is that when we find something, we can immediately alert the world, and they can train their eyes, ears, and scopes in on that and see what's going on. And a case in point on this is supernovas. Because of us, the book on supernovas has been shredded and thrown out. Sorry. It used to be you'd find 2 or 3 supernovas a year, and it was usually found by amateurs, because the professionals are all looking at certain places in the sky and doing their research. And it's the amateurs that are out there, standing and says, "Joe, look at that. Is that supposed to be there?" So I don't remember thinking. Joe says, "No, I don't think that's there either." And then they'll call in some friends the next night, and they all come say, "Yeah, no, we better report that." So they'll call like the police. I'm serious. And then the police will muddle around, well, who to report this to? Eventually it gets into some, academia someplace, and they'll report it, and then they go, and there's a supernova. And then the guy that first saw it, it gets, his name on it. And that was a very huge thing. Now, when a supernova goes off, it's a huge, bright explosion. And you can watch the different wavelengths of light that are coming off there, and it tells us things about what's going on in the cloud as it's moving off, in what we can extrapolate back and what's going on, in the first place. And if you think, you can see it like this. You see these light curves that are coming off, and then they slowly die out over time. Well, because of this, all we were seeing, because it's like a day or two after, all everybody was seeing was the light curves going down. Pan-stars came along, and instead of 2 or 3 or 4 a year, we're finding 1 a night. And not only that, we report it right away. They don't go boom and come down like this. They go boom, then go down, then another huge bump and come down, and then another one and come down. And the mechanism that's doing this, totally unexpected, in what's going on in a stellar explosion. And it told us an awful lot of the dynamics inside the star as well as within its environment. And that's just one thing that Pan-stars did, or I should say the data from Pan-stars allowed to do. And that's part of this rapid response, to be able to get this information out there quickly so that the big boys in the big island with the big telescopes can turn around and take a look at this and get more detail out of it. So that's just one example of what we do. Now, there's 2. There's a Pan-stars 1. This has been in operation science-wise for about 6.5, 7 years. Okay, it was constructed probably about 12 years ago. It takes that long to build these. The actual physics, just like the decast up there, it takes a long time. Actually, it doesn't take too long to put the structure and the mirrors and everything else together. Then it takes a couple of years just the science team to come in to figure out what do we have. When I point my telescope to this star, and it's not pointing at that star, why? What is it? How much do I have to compensate the motors for? When you tilt a telescope, it's the tons of glass, and that's going to deform on itself. How much do I have to push back on the actuators to make it rounder, or get its figure back, kind of a thing?
That's
all of this,
cozy.
yeah. All of this has to be figured out. Okay. There's a lot of stories I have, but I'll save them. I have a story about there's a 25-term equation, cosine of this minus sine of this, and it's 25 terms long, and it takes into account the trusses, the temperatures, everything, for able to do this. And it was John Tonray and can't remember the other guy's name, but they were up there with myself and Bob in the telescope, and they were having this really, Nick Kaiser, yeah, they were almost at fisticuffs. They were almost going to have a fight. They were just, and sort of this way anyway, but they're really arguing, and they're arguing this 25-term equation. Now, mind you, and I mean mind, can you imagine keeping that entire 25 terms in your head and what each term meant, and then arguing it? That's what they were doing. Bob and I were looking at each other. Whoa. Okay. Finally, one of them stops. I think it was John. And then the other guy stops. And silence for a little bit, and he says, I know it is. In the 21st term, that's supposed to be a plus, not a minus. And you want to know something? We've been running ever since. That was it. Of course, Bob turns to me and elbows me and says, I could have told him that all along. I just wanted to see how long it'd take him to figure it out. Okay, Bob. So now we're not the biggest telescope on around. We're a 1.8 meter, but it's big enough for what we need to do. It's specially curved. Its curvature and its figure is very special because what we have underneath here is a 1.4 gigapixel camera. It's the world's largest digital camera that we're allowed to know about. Okay, I am sure the boys next door to us have some larger things hidden around. But anyway, as far as the world is concerned, this is the largest digital camera. And it's got a sister, which is going into the second telescope, the second Pan-STARRS, which hopefully is going to be up and running here in a couple of months. So we're very, very close to going into commissioning with that. So one of the biggest things about this is that it's got a 3-degree field of view. In other words, most telescopes, this is sort of built opposite of most telescopes. Most telescopes, you build them so that they look very, very far into a tiny spot. Can you imagine take a survey if you're looking just at one little speck? You can't do it. So we wanted to take a large volume of sky at a time, each time we took a picture. But you lose resolution with that. So you make it up by having the world's largest camera. So what do we have? We have the world's largest wide-angle lens camera, right? So it's very, very special. It was very hard to get this together and flat all the way across. If you remember taking a look at wide-angle pictures, you can see the vignetting, on the side. We can't have that, okay? So we have massive corrector lenses and everything else to get this field flat all the way across. That is what took so long.
Well, I think since our fourth speaker is nowhere to be seen, we can both go. I'll go a little longer. You can go a little extra.
Good.
Too.
Okay, thank you. I was wondering about that. My stories always.
I think he's not here, so you get a little more of that.
I get a little more.
of the
Okay. Oh, that's good. Okay. Now,
unless he shows up.
then I'm in trouble. Then I have to really.
So it's up.
Okay. All cameras are black and white, even the ones you have. But they cheated. Instead of in front of each of your pixels, they painted a little red, one of them red, a little blue, and a little green. And so they read in 3 pixels, and then they form the colors out of them. Okay? And so if you have a 9 megapixel camera, you're going to get a 3 megapixel picture. Right? We can't lose any of our pixels. Every pixel is precious to us. Sounds like a saying that should go on the wall. So instead, we have filters. We have these big filters that we throw in across the camera. So if we want to take a color picture, we have to put in a red filter, take an image, put in a green filter, take an image, put in a red, put in a blue filter. Okay, combine them and then get our image that way. So we can't take a picture of anything that's moving fast. Okay, this is interesting. 0.5 gigabyte of data per second is right now streaming off that mountain down to our computers in Kihei. After this pipeline gets done with it, that 0.5 gigabyte turns out to be 7 times larger. 3.5 gigabytes of data is what we produce out of that image that's in there. And I love, they call this the reduced image. 7 times more that's inside of there. Okay. So some of the major projects, that was what we were doing before, was this consortium. Now we are primarily funded by a couple places. The majority of our funding comes from
we're going to start
NASA,
that just in a few
and
minutes.
that's
We're giving
for
it a couple.
NEO
It looks like our 4th speaker's not
and
here.
actually the first
number 2's
top
going a little
4
longer,
of these
and number 3
are
is going
all
to take
pretty
up some
much
extra
come
time.
out of
But
doing a
you're
search for
interested in that,
for asteroids.
Cool.
It's still the survey. It's still a survey.
okay.
We're scanning
Excellent,
huge chunks of the sky.
I am.
But in so doing, we're not just
Let's see. I'm
again,
just going to do a quick
capturing
once around
asteroids,
here and see how we're doing.
but anything else that's out there that's moving, okay, or doing something strange. So near-Earth objects, those are asteroids or
come and
things
squish in.
that are their orbits are
You can
coming
even come
close
in
to
a minute
us.
if you want.
It doesn't necessarily
But
mean
this
that
will be
they're
over in a couple
near
minutes.
us right now,
Okay.
but it means in time they're going to be, and therefore we better watch that.
JD?
If they're a little too scary, then we call them a potentially hazardous object. Okay?
So,
and those are ones where
a little late,
they're
and
not necessarily
pick up
going
the
to
rest
hit
of
us,
the time.
but they're coming so close
we'll
that we
probably
better
in 10
watch them
minutes
very
we'll ask
carefully.
you to funnel people in
Now,
as we open them up. Okay.
just because you find one of these once
Apparently
doesn't
apparently
mean
a lot
that's
of
the
people
end
in
of the
there,
book.
or a lot of people out here have no idea where the talk is.
Everything in space gets
So we'll open
perturbated
it up
by
in a few
everything
minutes.
else.
Okay.
Including, if it's a PHO, it's going to
See
come
my
close
friend.
enough that it'll be perturbated by
Get
the
a good
Earth's
picture
gravity.
with a close-up
change
of
its orbit.
these, right?
So, we find
Or
these.
even while I'm lecturing. Right?
We have to keep tracking. Because today this might be what their orbit looks like. But the Earth, the Moon, other things that they're going to pass by or go by could change their orbits. Okay? So these have to be watched to see what they're doing over time and if they've changed and have they become really hazardous. Okay? So potential PHOs and NEOs. Also, we're looking at anything that's in the inner solar system and outer solar system. We're finding a lot of what we call planetoids and other objects that are close in. Comets, I think we now have, we can claim 50% of all comets that are found in a year, we find them. Amateur astronomers are really mad at us. I'm an amateur astronomer too, so I don't like that. But, because of the survey, all of these things are popping out.
What do you think you have, maybe 10 more minutes?
Okay. Yeah, I should be able to do that.
I'll be back.
Okay.
Sorry to interrupt.
Yep. Supernovas, type 1As. This is a special kind of a supernova, of a stellar explosion. And it goes off in a unique way in which we can use the light from it and other features of it to determine precisely where it is, how far away it is. Okay, by looking at redshifts and other things. So this becomes what we call our standard candles. So one of our surveys today is we do a supernova. Well, there's a number of supernovas that are out there that we're watching. And so we camp out with the telescope and just take picture after picture after picture in different filters, and so we get information about that supernova. And this is building up and refining our yardstick to the stars, okay, for everybody in the community. In the community. As an observer, we sort of hate supernovas because the supernova observation takes about 8 or 9 minutes to do this, which is barely enough time for the observer to type everything in, to get everything ready, and then the next one is on top of us and says, oh, no. So you get 4 or 5 of these in a row, and you're underneath a table, and your keyboard is smoking, and you're blowing on your fingers. And whereas our normal chunks, when we're doing surveys of the sky, a normal chunk is anywhere from 30 minutes to about an hour and a half. As you can imagine, as an observer, we love those. That's enough time. Also, you might have heard of LIGO and gravity waves. We're part of both this and neutron detections to find the progenitors. So we go and search that particular area where they think it might be, and see if we can find something, for them. So we're also part of these as they come up. This is JD just left. This is one of his favorite. He got me this. This is an example of time domain astronomy. This is looking at the galactic core, and in a second you're going to, once my computer decides that it's going to actually run. Come on. What we are doing is we're zooming in at the very core, and we're going to watch. This is actual live data. These are stars over time, and you're going to see these move. Okay? I hope. 15 years. So it's one of the first times that we were able to. Let's go back. Getting back to, here it is. Let's see. So we're going to zoom into the galactic core. And then we're going to watch stars orbit. Now, we know there's a black hole that's in the center. You can't see the black hole. But it really doesn't want to do this, does it? But you'll see these circling, this object, and okay, and yep, I'm going to go on. But it was very nice, to be able to see this. Oh, here it is. Okay, I talked primarily about this data coming from Pan-STARRS to the IPP, and then from there it's analyzed, by our scientists and controlled from here. These are the filters that I was talking about, that go in. 6 different filters. Each filter is multiple of millions of dollars, to get that kind of glass. This is our shutter, and just to show you the size of it, they put pineapples in there. From that day forward, for 8 years, it's known as the pineapple slicer. These are the chips that are inside, our camera. So this is the world's largest camera. And just for perspective, that's the mirror that goes on top, or the lenses that go on top of this. So you can figure that's about this big. It's a huge, huge camera. Again, that camera is right here. So it gives you a perspective of what this looks like on the scope. The scope is leaned over this way. Okay. And I'm not. This is the moon. This is a typical picture that we would take. So it shows you the huge field of view that we have. Here's our center. This is upstairs. You can go upstairs and sit. 16 monitors. It gets very warm up there. And let's see. This is the area of the sky that everything in black is what we view on a routine basis. This is the galactic plane. There's too many stars in there for us to be able to detect things move or change. Yeah. Okay. Okay. Yes. So I think this is the end because I can't, just some pretty pictures. Yes, yeah. These are all taken by our camera. It took, I think, 167 images to put this one together. You have to take an image again in each of the different colors, enough of them to stack together to get it crisp, etc. So about 167 images to do that. And this is. I would love to do that. Thank you. Thank you. Okay. Oh, okay. Yeah. Oh, the end of it's up at the end of Lapoa Street. Yeah, MRTCB. Is this where it goes? No, where does it? Yeah, this is where it's supposed to go, right? Yes. Tiny URL. tinyurl.com. Yeah. And slash IFA. Okay, Joe. Slash IfA Maui. Where does this go? Oh yes, yes. I have Bella. Yeah. I got a cute. Oh, here it is. Yes. I'm sorry. Here we go. And then the other part. And then
You have the intro sheet
Yep.
that I just gave you? Okay. We'll do a sound check. Okay. This looks terrible. What's wrong? This is not how it looked before. How was it plugged in?
right over here.
Oh, there we go. It's good. Where's the, and we got the thing back in?
Yep.
Awesome. Yep. Beautiful. Thank you. Okay. I'm going to open this up. Oh, yes. Let's just switch to on.
Check one.
Okay. Go ahead and grab a seat. Okay, JD. We lost a lot of our people in our room. We went way over, I think. And we are about to start. Can you
Check
herd
one.
some people in? Well, it was full a minute ago. Most people don't know where this is, so if I put the time in to put it together, maybe we can tell people with where it is. Yeah. Pardon me. Huh? Pardon me. And I'm going to actually open this door up for a minute here, if I can. Thank you, Mark. Okay. Hi, how are you? What's that? It's this one. Right here. It's about to start. It's about to start. Yeah. About to start. Come on in. There are chairs. Welcome to the Institute for Astronomy. Next talk is about to start if anybody's interested. And I'm going to go ahead and start. Okay. Okay. I think we're good.
I got no sound here yet. Check 1, 2.
Okay.
This is on, but no sound.
Great. Since we're running a little behind schedule, everybody, we're going to go ahead and start the next talk here.
Check 1, 2. Check.
And
Check 1. Check. You got it?
can you hear? Okay. Okay.
Nothing on the PA though, right?
Good.
Is this coming over?
Maybe we'll leave it open. If it gets too noisy, feel free to close it. Okay.
Is this on? Stefan, is this on?
Okay, we can close this a bit.
Check 1, 2. Hello? Over here.
But you're not amplified.
He's not amped yet.
So we can't hear you.
Oh, so there's nothing. There's no PA in here.
There's no PA.
Hello, everybody. I'm Mark Willman, and it's my pleasure to introduce Dr. Joe Ritter. He has 4 degrees in physics, wow, and is a multidisciplinary student of the cosmos. He began his science career developing techniques for imaging inside living cells, worked in birth defects research and biochemistry, did research in artificial intelligence, then genetics. After high school, he decided to go to college and study physics and math while running a computer business. As a student, this is a lot of stuff, Joe. You've been very busy. As a student, he studied space physics in the University of California, San Diego. Then at the Center for Astrophysics and Space Science, he was associate development engineer. He ran a lab developing novel space plasma flight hardware and was part of the first Hubble Space Telescope service mission. As a doctoral student, he developed novel optical instrumentation and computational techniques for measuring optical scattering for satellite oceanography for research in radiative transfer for climate change. Very topical. Performed the first solar areal scattering measurements ever made at sea and simultaneously co-PI'd at the great genotoxicology and biological radiation dosimetry payload for Space Shuttle mission STS-91. After his PhD, Joe was associate research scientist in space systems engineering at the Florida Space University.
System So economic growth is really depleting our natural wealth, and even hurting us directly here on Maui. So I think adding space resources can help us sustain economic growth, and starships, if you could build them, that have to recycle everything, will push green technologies on Earth to be developed. Now here's an old view graph from a few years ago. I said we will find a habitable extrasolar planet, a new Earth, soon. So this was my 2013 view graph, and I said there will be 10 billion of these just in our galaxy alone. Now we believe that there are probably 100 billion, that every single star we see may have a habitable planet. This has not been known for more than 5 or 10 years. It is now, maybe in the last 5 years, scientists have said, wow, almost every single star may have a planet that could support life. That's incredible. And one was recently found, right? And our closest star has one, Proxima Centauri b. So consider that our global GDP is $69 trillion, roughly. Consider 10 to the 10th stars with that, and consider 10 to the 10th times that knowledge. If we could somehow, look at this or tap this, I mean, this is an amazing resource, the galactic knowledge base. There's a habitable planet, Proxima Centauri b. It's approximately 4.3 light years from here. We've known about it since 1998, but it's only in the last few months that it's been public that it's actually, there's a habitable zone, meaning there's liquid water, and we could possibly have Earth. And it looks like there are a lot of planets like this around red dwarf stars. 4.3 light years, how far is that? A light year is about 6 trillion miles, roughly. So it's pretty far. So maybe we should go find this life, right? We are building telescopes to look for it. And upstairs you can see Kevin is talking about our Planets telescope, which is for developing technology for finding life on other planets. It's not a very big telescope. We're recycling an old building. We're being very environmentally minded about it. But some of us are actually interested in going to places like that, not just finding it. Okay, you've all heard of extinction level events. You've seen these movies with big asteroids and things. And so in Chicxulub, there's a giant crater in the ocean off the coast of Mexico, and a comet traveling 30 kilometers a second, so 150 times faster than a jet airplane, hit, slammed in, sent up debris everywhere, and killed all the dinosaurs and a lot of the life on Earth. Could this happen again? Yeah. Will it happen again? Yes. The question is when, right? We know from the fossil record that roughly every 26 million years there's an extinction event. Impacts happen all over the globe. You can see them if you go places. Here's a picture of a real one. This one's in Arizona, but we see sites like this all over the planet. There was an event in Russia in 1908 in Tunguska. There was a 15 megaton airburst. To give you an example, the atom bomb used in Hiroshima was about 16 kilotons, so 1,000 times that size. This is just from a rock coming from space. And so it devastated a large area in Siberia, and I've overlaid this on Maui just to give you an idea of the size. So the Tunguska DA-14 near miss, it didn't even hit. It was going so fast it blew up in the atmosphere, released the equivalent energy of 15 million tons, and so this is the blast area. And then here's the dust blast area, larger than that. So this can and will happen. That's one reason to build starships, right? Another is the ultimate fate of the Earth is the sun is going to stop burning its hydrogen fuel and start burning helium fuel, and it's going to expand. And the crispy future of Earth, very simply, is that the sun will expand to about Earth's orbit, and it will cook the Earth, and this is what Earth will look like, and this is what the sun will look like, and this is 5 billion years from now, so don't worry. Okay, but we probably want to think about this if we care about humans going on. Maybe we don't. I don't know. So to give you an idea of scale, how far have we gone so far? Well, we've gone to the moon. How far away is the moon? Anybody? We're going to do Socratic method here, where I say something and you talk back, and yeah. Pretty close, right? So it varies. It's an elliptical orbit. Nominal radius is 238,000 miles, so 250,000 miles, right? So how far have we gone? 239,000 miles, roughly. And it was the fastest manned vehicle ever, the Apollo spacecraft. It's 25,000 miles an hour. And so it had what's called a specific impulse. We're going to start with the rocket science stuff here. 450 seconds. And that just means the fuel ejected out the back is going 4.5 kilometers every second. So it's pretty fast, but that's a chemical rocket. We are interested, you saw Gary's talk earlier, some of you saw it, and Gary and I are interested in situ resource utilization, going to the moon, getting water, because there's water on the moon. As part of that experiment that was done, they sent an impactor and it crashed in the south pole of the moon, and we made measurements from the top of the mountain here as well, and there's water on the moon. So what can you do with water? You can make rocket fuel, you can breathe, you can make concrete, you can split it into oxygen and hydrogen. You can do hydroponics and eat. You know, if you have water, you can do anything. You can do nuclear fusion for fuel, for energy. So you can just travel anywhere you want if there's water on the moon, and there's water on the moon. So some of us, this is me working with Neil Armstrong's old suit in Smithsonian, and Gary showed you this cool picture of the space station. So there are resources out there for doing these things. What's the fastest anyone's gone? Well, a robotic spacecraft. Who among you remembers Voyager 1 and 2? So these are the fastest spacecraft ever made so far. Is that right? Is Pluto Express faster now with ion engine? I think these are faster. So they're going 35,000 miles an hour. My old truck got me up here about doing 45. The old one blew up, and the new one goes about 45. So that's pretty fast. So where are these spacecraft now? Well, here's the sun, and here are the outer planets, and then far away from the sun is the heliosheath and then the heliopause, and out here's interstellar space. So when I first did this view graph, they were both inside the heliosheath here. Now Voyager 1 has actually gone on the other side. So we can measure a difference in magnetic flux and particles, and so there's some cool science still coming out of Voyager. Very low data rates, and the radioisotope thermoelectric generator is almost dead, but there's some data coming from it, low bit rates. So we have stuff that's gone just outside of the solar system, but certainly nowhere near another star. There are daunting technical challenges. What are these challenges? Well, the first one, it's far away, right? Our closest star, Proxima Centauri, is 4.3 light years away. So that is 25 trillion miles, something like, I don't even know what that means, right? Give you an idea of scale. Speed of light, it's so fast, it's, if you were to go around the Earth about 7.5 times in a second, that's how fast the speed of light is. You could go to the sun in 8 minutes, okay? We're talking going that speed for years just to get to the closest star. So these are huge distances. Presumably we'd like to do it maybe with people, and so you want to do it in a lifetime so you can make it there so you aren't dead, you know, when you get there. And it takes enormous resources. So fuel, power, food, air, water. You can't stop and pick up these things at a 7-Eleven. You've got to bring it all with you. You might be able to pick up some dust on the way. Maybe you can mine some asteroids while you're out there. Mark will tell you about that. Biggest problem right now is radiation damage to DNA. Did you guys see the movie The Martian? Okay. Pretty good. One of the things they got wrong in that was the radiation dose. Everybody have cancer, right? I mean, right now we just do not have technology to get people to Mars with typical engines and long trips, years in space without everybody getting cancer. It's an unsolved problem. There are social issues. I mean, people can't even get along on a big planet with lots of resources. What if you have a bunch of people in a little confined space, and you know, what kind of government do you have, and then do you allow them to breed with each other, and then do you get cliques, and so you have to say, no, we don't have enough genetic diversity, you and you have to mate, and you know, all kinds of issues, right? So there are social problems to look at. How long would it take to get just to our closest star? Well, if you're going, distance is velocity times time. So I'm going to have a few equations, not too many. Voyager's going 35,000 miles an hour, so you can break out your calculator. It's going to take 80,000 years just to get to the closest star. And that's the fastest thing we've ever built. So yeah, do we have the technology? No, not even close, not yet. So we need velocities that are, you know, maybe 1/10 of the speed of light at least. An interesting quote from a letter from Galileo to Galileo by Kepler. Let us create vessels and sails adjusted to the heavenly ether, and there will be plenty of people unafraid of the empty waste. They're talking about space travel. This is back in the 1500s, or early 1600s. But in the meantime, we shall prepare for the brave sky traveler maps of the celestial bodies. I shall do it for the moon. You, Galileo, do it for Jupiter. And Jupiter has these moons, and Galileo got pictures of them and drew them and computed the orbits of them. These guys long time ago, we're talking about going to other stars. How do you go there? Well, some people say solar sails. You guys have probably heard of Arthur Clarke. Arthur Clarke and Bob Forward described solar sails, not cells, but sails, as a good way of achieving space travel. And so, in fact, when I talked to Bob a few years ago, he put up this picture of a giant antenna beaming energy to a spacecraft to push it along. And the antenna he put up was 6 times the diameter of Earth. And I said, Bob, how are you going to build this? And he said, Joe, I'm going to retire. That's up to you. Right? But people have been looking at these visionary ideas. Well, some of them are coming to fruition. Charlie Chafer is another friend. He built a mission for NASA that was called Sunjammer. And Sunjammer has a big solar sail on it. And unfortunately, NASA killed this mission a few years ago. It was a great mission, really cheap. But Charlie was in this month's Smithsonian magazine, so I thought I'd just throw it in. We do public outreach here. J.D. Armstrong, Dr. Armstrong, you see walking around with the tie. He does public outreach. So my friend Charlie did this. This is an article about alien outreach and doing this with renting time on big telescopes and sending pictures of DNA and things like that. So if you're interested in this stuff, go look at this month's Smithsonian magazine and see what Charlie's been working on a long time. But the solar sail they developed was this big. It's 1/3 of an acre, weighs 70 pounds. Wow, so sunlight can push it, right? Great way to do interstellar travel. So a question I think about is, what's the best way to accelerate this? How can you maximally accelerate a solar sail? There's something called an O-berth maneuver. And so this is what you do is you take your sail, we go in near the sun, and it pushes it really hard, and then it shoots it out. But right when you're here, as close as you can in the gravity well, you dump all your fuel, and you do all the propulsion you can, and you run all your engines too. And if you're really smart, you make a solar sail that ablates and throws off material too, and you get a lot more out of your propulsion. And so with an O-berth maneuver, you drop in close to the sun, you make your delta V burn right by the sun, and you get this big multiplication. So this is maybe one of the practical ways to send small instruments to other stars. I try never to put very much math in talks. And there's a reason, because people, kind of glaze over and, right, it's an equation. I remember I had one of those years ago in school. I didn't like that. But math is beautiful, and it's a language. And so another quote from Dick Feynman, it's impossible to explain honestly the beauties of the laws of nature in a way that people can feel without their having some deep understanding of the mathematics. So I'm sorry this tends to be the case, and I have to show you a couple of equations in tonight's talk. So here's Rocket Science 101. I need a demonstration. You, sir, could you help me? All right. So when you put your hands up like this, okay, and push me. Okay, so I moved, but you also moved back. Great, thank you very much. Okay, so for every action, there's an equal and opposite reaction. So a rocket works by having some fuel inside it here, and it shoots it out the back one way, and the rocket goes the other way. Right? So this is Rocket Science 101. You shoot fuel one way, the rocket goes the other way. Conservation of momentum. Right? Okay. You can write the equations for it, but we don't need to go into that. Rocket Science 102. If you apply a force and you have a change in your mass because you're losing fuel, and then you have a change in your momentum because you're speeding up, this is your rocket thrust equation. So it says your force on this rocket is given by the rate of change of your fuel. You're shooting your fuel out the back, right? Okay, and I won't go through everything, but basically, if anybody's interested in the math, we'll talk about it afterwards. And I'm gonna just use these windows here so I can think. I think that they are doing rockets out there. Okay. So I won't go through the whole thing, but the whole change in velocity of a rocket is proportional to how fast you can shoot out the fuel. So you can imagine I've got a certain amount of fuel. If I throw it, if I throw it faster, I'm pushed further and faster the other way. So the faster I shoot out my fuel, the further I can go. That is to say, the ultimate velocity and range of a rocket is a function of how fast you eject the fuel. It's all about how fast you eject the fuel. Faster you do it, the further you go. So that's Rocket Science 102. rocket science, sorry, that's rocket science 103. Now you know lots of rocket science. We need really high velocities, so our velocity is limited by the ISP, how fast we can shoot out our fuel. We must carry all the energy with us, and current chemical energy systems, like the space shuttle, which is now grounded, is liquid oxygen, liquid hydrogen. It's all chemical. There's only so much energy you can get from chemical stuff. So people look at nuclear or other things. So again, the rocket is limited by the amount of energy. Here's a plasma rocket engine. Franklin Chang Diaz is an astronaut who's actually a plasma physicist. And so his rocket engine is fairly impressive for going to places like Mars. You shoot in a neutral gas, you heat it with a helicon, it's like radio waves, and then you have a superconducting magnet here to squeeze it, and then it expands and goes out the tail and magnetically disconnects, and you have thrust. So it's a plasma rocket. So you're ionizing the gas. Plasma is ionized gas with structure. That's the definition that Hannes Alfvén always used. He got a Nobel Prize in plasma physics. And the stuff glowing inside fluorescent lights when they're turned on, that's plasma. Okay? This is great, but this is only 50 kilometers per second for the fuel. Great for going to Mars maybe in a couple months instead of 6 months or a month. Not good for going to other stars. So another idea is a fission fragment rocket where you have a nuclear reactor and you take nanometer-sized plutonium dust in here, and it reacts. And this laser's not working very well. I wonder if anybody in here has a laser. Does anybody back there have a laser? Do you have a laser? Do you have a laser, Mark? No? Okay. I'm going to do this. Okay, so the plutonium, it's a fission reactor, and so you take these microscopic pieces of dust and they eject out the back of a rocket. So it's one idea. Then there are fusion rockets. Thermonuclear fusion is the way the sun gets energy. If you could take the heavy water out of a gallon of water from the seawater, take the heavy water out, maybe 1 part in 5,000, and burn it in a fusion reactor, you get as much energy as 300 gallons of gasoline. The core of the sun runs on taking hydrogen and ramming it together and fusing it together and making helium. It is possible you can make a hydrogen fusion rocket. And so some friends of mine made a design for this, and it looks like you still need a 1 billion kilogram rocket, but you can go maybe to Alpha Centauri in 100 years. And so this is taking laser beams and imploding hydrogen pellets to make enormous energy from nuclear fusion. It's still a really big rocket. And so here's a picture of their design. This is from the Icarus Interstellar guys. They're a spin-off of the British Interstellar Society. Those are the guys that in the 1920s planned on how to go to the moon. And everybody thought it was crazy then. Well, they've done it. How big is it really? Well, this is their design compared to the biggest rocket ever built, and this is the Saturn V. Took people to the moon. How big is it? Here's the Empire State Building. So you go, wow, that's huge, but you know what? We could build a building like that. Maybe you could build a starship like that. Not outside the realm of what could be done. I mean, yeah, it's enormous. Yes, it would take incredible resources. Is it doable? Yeah. Is that maybe the best design? Not necessarily, but these guys have done a great job working. These are serious engineers that do this for a hobby. Okay, but still, it's a little slow. So the best, we said that the best way you can, the faster you shoot out fuel, the better. What's the fastest thing that anybody in here knows of? Anybody? Light, yes, right. So if you can shoot out light, that's great. But you have to get a lot of thrust. So how do you have a lot of energy and make pure light and energy with it? Matter-antimatter collisions, right? We've all seen Star Trek. They have an antimatter reactor. Well, okay, I know it's getting a little out there, and we can produce antimatter. We do produce antimatter all the time. It costs about $1 trillion a gram right now, but it turns out there is a better solution to it. It turns out the Fermi Gamma Ray Astronomy Telescope discovered that thunderstorms make gamma rays. And so these terrestrial gamma flashes, there's antimatter that is created. And so they bombard, these gamma rays bombard the upper atmosphere of planets and the interstellar medium and make antimatter. So it's there to be harvested. So maybe you don't need to make it in a giant reactor. Maybe you could just go harvest your antimatter and use it for propulsion. And then you have anti-electrons and and electrons, and you combine them, and you make your own gamma rays, and you shoot them out the back of your spacecraft, and you've got really good propulsion with the highest ISP possible, maybe 3 times 10 to the 7th. Speed of light, use light, right? So these things are a little out there. This was a NASA Innovative Advanced Concepts program to study some of this stuff. So in the intro, it mentioned I was a NIAC fellow. We look at crazy things like this because it's possible to do these things. Okay, once you're going fast, what are the problems? Well, dust grains. So a typical dust grain that you see in interstellar space is 10 to the minus 12 grams. So that's a thousandth of a billionth of a gram. So it's a millionth of a gram, okay? Or a billionth of a milligram. If that hits your spacecraft at 10th of the speed of light, it's like a stick of TNT. So you need some kind of shield, right? I mean, the problems of going this fast, anything, even something, a nanoparticle hits you, it's a giant explosion. So shields are required for this sort of thing. Okay. So, I mean, we really do look at these problems. I know it sounds crazy to go, well, can you go to another star? But these are the challenges, and we're looking at how to solve these things. Of course, the university won't pay me for this. Right? Radiation is a big problem. I got this view graph from my friend Shane Westover at Kennedy Space Center, and people look at giant superconducting magnets to shield astronauts while they're out there. There are some designs, there are some design issues, but people are looking at how to solve the radiation problems. But then you go, well, we've all seen Star Trek, right? Who here has seen Star Trek? Okay, so I admit I watched it when I was a little kid, right? Can you travel faster than the speed of light? Well, everybody says that is violation of Einstein's 1905 paper on special relativity. It's actually not. It's a violation of causality and cause and effect, but it doesn't violate relativity theory. So, for this, a relativity primer in one view graph here. Here I'm plotting velocity horizontally, and here I'm plotting mass. And as you go faster and faster, your mass increases. Really, it's technically more correct to say your momentum increases. And you can't go faster than the speed of light and carry useful energy with you. But are there ways that you could go faster than the speed of light? It's an interesting question. It's not a violation of relativity, regardless of what some physicists will tell you. And here is a bizarre experiment at CERN in Geneva, big particle accelerator. You guys heard about the Higgs boson and stuff like that, where they reported that certain neutrinos were apparently than the speed of well, I have to tell you, this was a timing error mistake, but I just threw the view graph in. People got really excited, and they went, no, we can't throw Einstein out the window. This was not real. Okay, next. Maybe through some exotic physics can you go faster than the speed of light? Well, one way is to have a traversable Einstein-Rosen bridge. You may have heard of something called a wormhole. Okay, that's the more common term for this sort of thing. So what if you have a star with low mass, you have the gravity deformed space-time. If you have a really high mass star, gravity will deform space-time a lot. The idea is that possibly you could deform it so much that you make a hole going to another spot. So essentially it bends space-time, and so instead of traveling around in this four-dimensional matrix here, you just kind of go through the wormhole and go take a shortcut. The problem is, it's believed usually you might get crushed to an infinite density when you go through that, so that's no fun, right? You can't carry information with you when you get crushed to infinite density, and you get spaghettified and stretched out as you fall in. But are there ways to do it? Well, maybe if there's a rotating black hole, and maybe if you have exotic matter propping it open so you don't get crushed. Not sure. Okay, maybe. We're kind of going into breakthrough physics stuff here that's not known. We've never detected a wormhole. Some people believe, many physicists believe it is possible to have a wormhole. We know that there are black holes. And in fact, it turns out that Einstein-Rosen bridges are handy tools for time travel, and maybe I'll give another talk on that another night, because I don't want to take up the whole evening, because I want to get Mark in here soon. There is something called an Alcubierre warp bubble, and So here's one way to go faster than the speed of light. Be in a space-time bubble, stretch the bubble so that the bubble itself is being pulled faster than the speed of light, but inside the bubble, the space itself, or you yourself, are not going faster than the speed of light. The bubble and space-time can go faster than the speed of light. That doesn't violate relativity theory. But as long as inside that space-time bubble you are sublight, you can do this. It theoretically works, although this takes enough negative energy to do this that's like the size of Jupiter. And of course, we don't even know what negative energy is. So I go to my theorist friends and go, you know what, I'm an experimentalist. I want to build stuff. Nah, don't think so. So let's talk about real science. Did any of you a couple years ago, raise your hand if you did, there was a big thing in the news about NASA and warp drive? Yes. Okay, one of you heard that. So that was Sonny White, and I was talking to Sonny earlier today, actually. This is Sonny showing me how to do a double loop in the space shuttle simulator, which you can do a double barrel roll when you land. Amazing. I didn't know you could do that with the space shuttle. Apparently you can. And so he works in an breakthrough propulsion where they're looking to do something space-time. So Alcubierre warp drive idea, if you can do that, but you oscillate the matter, and you have it in a certain configuration, in a toroidal configuration, turns out you can do it with the amount of positive matter of like a Volkswagen instead of a planet. You start going, I don't know. I mean, it's still impossible, but it's far less impossible than a planet's worth of positive matter. So maybe it's a little less crazy. Don't know. Something to think about, right? So they have a whole program where they're looking at trying to do low thrust and actually seeing if they can measure these effects. Now, there's a lot of junk science in the media. I have to say Sonny is a good scientist. He's never made any claims that you can do warp drive. That's the media. He's actually a good physicist and made no claims about anything like this. I went down and worked with him on stuff to be really careful with the experiments. So I was down in his labs, Eagle Works, down in Kennedy Space Center. And but they actually have a whole idea of how you could do it. So what would it look like? Would it look like this? No, and here's why. According to Sonny, well, first of all, the warp bubble from this, it's the wrong shape, and then, you don't cover the front of your spaceship. So sorry, Star Trek fans. I mean, it's great, we love it, but nope. You'd probably have to look something more like this. And again, I'm not saying this is possible. I'm just not saying it's impossible. There are people looking at these things who are real scientists. And so it's a toroidal containment of this oscillating negative energy, and the spaceship doesn't stick far out, and so there's a bubble around it. So it's sort of a modified Alcubierre thing. There are other schemes. I proposed years back in a publication a solar sail with a giant inflatable telescope where you can first ablate your solar sail, then you can use the sun to vaporize material to push it, and then you use microwave generators to push it, and then you have a giant telescope and a starship that you can do a lot of things with. And you can come to one of my other talks on giant space telescopes sometime if you're interested in odd technology. People talk about generation ships if you don't want to go fast. Printing life. Synthetic life. We're on the verge of being able to make DNA in synthetic cells, and you could probably send a little thing to another star. I'm not sure about the ethics of some of this, but the technology is virtually there. What are social challenges? Well, I mentioned earlier genetic diversity. So you have to have a lot of people so that people can breed if you have this generation ship. Can the people get along? I don't know. That's a tough one. That's probably tougher than solving the radiation problem. Will the people evolve or devolve over time if it's long? I don't know. I'm going to end this by saying, why should you go somewhere? Well, maybe we're not from here. And here's an interesting idea. So there was a study done where they looked at DNA base pair complexity, and any information storage. If you understand why, come talk to me afterwards. They plotted the complexity versus time of DNA on Earth. And to extrapolate back down to zero complexity, when life might have evolved, it's a billion years. The problem is, Earth is only about 4.6 billion years old. One interpretation of this data set is that the DNA that we see on Earth, in early Earth, here's the beginning of Earth, right? Here's where Earth started, actually came from somewhere else, that possibly Earth was seeded from an alien civilization. I'm not saying that's the case, but I'm saying this data set, and this is good genetic stuff here, supports that possibility. So maybe DNA is supposed to just make more DNA. That's why all of you have kids and grandkids, and that's DNA's job, right? So maybe we should go find life somewhere, is what I'm suggesting here. Thank you, and do you have any questions? Okay. Yes. Cool. Okay. Strangest talk ever given at IfA, probably. Yes, cool. There are lots of things that will make it a little more efficient. Still, even fusion, there's a limit to ISPs you can get. And in a minute, Mark's going to give a talk on asteroid mining. Any other questions? Going to other stars? You learned it all. Okay, great. Thank you very much. Okay.